So we've got a setup here for looking at standing waves on a string. On this end, this is a digital function generator, so this is making sine waves, or it will be when I switch it on. And I can change the frequency, so we can set whatever frequency sine wave we want. And then the signal from that is coming out and going into this, which is basically essentially like a speaker. When we turn the power on and send a signal to this, it will vibrate up and down at whatever frequency we have set, and the end of this rod will move up and down as well. You can see there's a string tied around the rod, and then all the way down at this end, we've got a pulley, and there's some weight hanging off the end, so we can change the tension in the string if we want to. But the main thing is we have this string set up with some tension, and we can shake one end. So this end of the string is at about 170 centimeters on the ruler. The other end is down at the 0, and if I go to the middle of the ruler here at around 85 or so and give it a pluck, we can see the whole string bounces up and down. Okay, so next I'm going to turn on the function generator and we'll take a look what happens. Right now it's set to just over 10 cycles per second. So you can think of that as 10 times a second, this thing is moving up and down through one cycle. When it does that, the wave travels down the string and bounces off that end with the pulley and comes back to here. But it just so happens that I set this up so that the time it takes for that wave to go down to the end and bounce back, right when it gets here is when the next cycle is starting from the output. And so each wave builds on the previous one, and you end up with this energy buildup and this thing bouncing away like this. So that's the thing with the standing wave pattern like this, it relies on some very specific conditions being met. Namely, that the time that it takes for the wave to go all the way down and back is the same as the time between cycles here. So each consecutive wave that goes down and comes back adds up with the next one from the function generator. And that's why this energy builds up to this large displacement like this. So if we change the frequency or we change the speed of the waves, then we can change either one of those and that equality won't be true anymore. So if I come over here to this side and I pull down on the string a little bit, you can see the string is still kind of bouncing around some, but we don't have that big pattern anymore like we did. And when I let go, it builds back up because we're still putting the energy in from the function generator. So when I pull down on the string, I'm increasing the tension, which speeds up the waves, so then they get down and back faster than they were before, and they don't add up anymore because they're getting back too early. Similarly, I can lift up, slow the waves down, and then they're not adding up because they're taking too long to get back, so they're not syncing up with the next one. So that's changing the wave speed by changing the tension. Let's take a look at what we can do by changing the frequency. So here at the function generator, I can slowly adjust, turn the frequency up. You can see I haven't changed it too much, but we're still getting some oscillation. But once I get to sort of 11-ish, it's bouncing around, but nowhere near how it was. But if I keep going up, 12, 14, 16. Okay, something's starting to happen now on the string. And that's getting a little louder. If I put it right around 20, you can take a look, and now instead of a half wave fitting on the string, we're fitting a whole wave. So that means by the time one wave goes out and hits the end, the next one is coming already. And so then when this one, the initial one, bounces and comes back, it's going to have skipped one and add to the next one. So now basically we can fit a whole wavelength on the string, and we've got constructive interference with a node in the middle. So if you look here, right around the middle of the string, there's this point that's hardly moving. I mean, if I put my finger here, I can feel it buzzing. But if you look off to the side, it's moving a lot less than the string around it. And taking a look in slow-mo again. A cool thing we can do here, since we're putting two waves onto the string in the time it takes for one wave to go all the way down and back, what we can do is cut the string length in half by pinching it right here. I can stop this side, and now you can see a little bit of vibration gets through my fingers to the other side. But if I hold this here, we're now at the fundamental for this half-length string. So because we were sending two waves for the time to go down and back, that's the same as sending one wave in the time it takes to go from there to my finger and back. We can keep turning up the frequency from here and squeeze more waves onto the string and watch what happens. So that was 20 hertz. And as I get up to around 30, you can see now we've got 3 antinodes and 2 nodes, well 4 actually counting the ends. So node, antinode, node, antinode, node, antinode, and node. And so now we're putting 3 waves onto the string in the time that it takes for one to go down and back. And so the way that those add together is you get this amplitude pattern that's sort of 3 half wavelengths like you see here. We can keep going up with the frequency and see what else we can see. So that's 30. If I turn it up to 40, we can fit even more on there. And we can keep going up even higher, but at higher frequencies, the antinodes tend to be a little smaller and harder to see. So I'll probably stop here. Maybe we'll do one last slow-mo look at this one.